Hello everyone, this is Rain, and today I'll be introducing my 15300 project proposal to you. Let me start by first introducing the group members in this project. My mentor is Professor Elaine Shi, and she's an associate professor in the computer science department. Her interest is in security, cryptography, distributed systems, randomized algorithm, and programming languages. Since 2011, she has also been doing research on cryptocurrencies and blockchains. I'll also be working with two other students from 15300, Mike and Marcia, and we'll collaborate while making our distinct and significant technical contribution in the project. This project focuses on oblivious algorithms. With the increased use of outsourced storage and computation, privacy of the outsourced data has been of great importance. A canonical setting is where a client with a small local storage outsources its encrypted data to an untrusted server. In this setting, encryption alone is not sufficient to preserve privacy. The access patterns to data might reveal sensitive information. Oblivious algorithms are a class of privacy-preserving algorithms whose access patterns do not leak sensitive information. To give a little more background, there has been some prior work exploring the design of parallel data oblivious algorithms using the PRAM model. However, it is widely understood that the vanilla PRAM model might not best capture modern multi-core architectures. As a result, in order to better account for the synchronization cost, a long line of work in Professor Shi's group adopted a multi-threaded computation model in which parallelism is expressed through paired forks and join operations. So binary forks spans two tasks that can execute in parallel. On the other hand, its corresponding join is a synchronization point. Both of the spawned tasks must complete before the computation can proceed beyond this join. Such a binary fork join model is also adopted widely in practice. And in this project, we will optimize, evaluate, implement, and open source efficient oblivious algorithms and data structures on this binary fork join model. There are a few things we hope to accomplish next semester. First, we want to implement the vanilla version of a sorting algorithm as a simple reference algorithm. The biggest challenge in this step is that a thorough understanding of the paper and its core ideas is required. Given this is an independent research but not a traditional class, I assume I have to study by myself instead of being lectured. So this could involve a lot of readings and searchings. Secondly, we hope to implement the oblivious version in the parallel model. The biggest challenge in this step is that although the algorithm design is finished in the paper, no one has ever implemented on real computers. Therefore, if real-world settings and theoretical assumptions do not match, a lot of additional works need to be done, such as revising the model to adapt to current hardware. Thirdly, we hope to implement a non-trivial, non-oblivious version. Previously, quicksort is used for comparison. However, real-world storage media such as disk support sequential accesses much faster than random seeks, and quicksort does not support this kind of locality. Therefore, we had to find another algorithm that has this property. Although a modified merge sort could be the potential solution, there's a lot of room to explore and do research on. Experiments on different sorting algorithms may be needed. Lastly, we hope to provide library support in C++ or Python that contains reference implementations for oblivious sort. Hopefully, this could be relatively easy if the previous steps are successful. In theory, some of our data oblivious algorithms asymptotically outperform the previously best-known insecure algorithms, while the rest matches the previously best-known insecure results. Therefore, it is very possible to improve the state-of-the-art algorithms for some well-known problems and application. For example, our algorithm asymptotically outperformed the previously best-known results in the binary fork join model for tree contraction, connected components, and minimum spanning forest. So there's a lot of room for potential applications in, say, like navigation systems or something else. And here are some references for this project and the presentation. And that will be all for today. Thank you all for listening.